Bismillah ar-Rahman ar-Rahim. This is lecture 15. This is the last lecture of the course, and it's about complex matrices. So we'll be talking about Hermitian and unitary matrices. Of course, the first part of the chapter is on complex numbers and complex arithmetic, which you have studied in your math courses. So one important difference between real vectors and complex vectors is in taking the dot product. For example, the length squared of a vector must be real. For z equal to a plus ib, where I is the square root of -1, the norm squared of z is equal to z times z conjugate, which is z bar. So it is a plus ib times a minus ib, which comes to a squared plus b squared. For a complex vector, z having z1, z2 to zn, this becomes the norm squared equal to z bar transpose times z, which is z1 bar, z2 bar, zm as a row vector times the column vector z1 up to zn. So this is the norm squared. So the definition of the length of z, it is the square root of the norm squared, which is the norm of z1 squared plus zn squared. To simplify the notation for z transpose conjugate, see we have the vector sign over the letter, and then we have the bar, and then the t. So too many symbols. To simplify that, we just use the capital H for the bar transpose or the conjugate transpose, and we can still use the arrow designation for vectors above the letter, indicating that they are complex. So this is usually read Z Hermitian, okay, instead of Z transpose conjugate. For a matrix, we take the transpose conjugate when we transpose a complex matrix. So A conjugate transpose becomes A Hermitian. It is pronounced A Hermitian. For example, A, which is A1i, 0, and 1 plus I, becomes A Hermitian. It is the transpose. 1i becomes 1 minus I in the first column, and 0, 1 plus I becomes 0, 1 minus I in the second column. So now, complex inner products. For real vectors, we know that the norm of x squared is x transpose x. Now for complex vectors, it is z Hermitian times z. So definition of the inner product of real or complex vectors u and v is u Hermitian times v. So it is u1 bar up to un bar times v1 vn as a column vector. So it is u1 bar v1 plus u2 bar v2 plus un vn bar. Okay. With complex vectors, u Hermitian v is different from v Hermitian u. The order is now important. It is the complex conjugate of u Hermitian v. Okay. So they are not the same. As an example, the inner product of u, which is 1i, with v, which is i1, is 1 minus i1, which is 0, not 2i. If we left it as 1i, so i1 becomes 2i, which is incorrect. So the correct is u Hermitian v, which is 0. Example 2, if u is 1 plus I and 0 and v is 2i, then u Hermitian v gives 1 minus I, 0 as a row vector times 2i. The column vector, it is 2 minus 2i. In example 1, the vectors u and v do not look perpendicular, but they are. a zero inner product still means that the complex vectors are orthogonal. Similarly, the vector 1i is perpendicular to the vector 1 minus I. Okay, it becomes 1 minus I times 1 minus I. It is 1 plus I squared, which is 0 because I squared is minus 1. The inner product of AU with V equals the inner product of U with a Hermitian V. Okay, so AU Hermitian V becomes U Hermitian A Hermitian V. Okay, the conjugate transpose of two matrices A times B is AB Hermitian is B Hermitian times A Hermitian. Among real matrices, the symmetric matrices have the most important special class A equals A transpose. They have real eigenvalues and a full set of orthogonal eigenvectors. The matrix of eigenvectors S is an orthogonal matrix with orthonormal columns. It is Q. Every symmetric matrix can be written as A equal to Q lambda Q inverse or A equal to Q lambda Q transpose. Now, for complex matrices, the special class consists of the Hermitian matrices when A is A Hermitian, where Aij is equal to Aj conjugate. Every real symmetric matrix is Hermitian. If A equals A Hermitian and Z bar and Z is any vector, the number Z Hermitian Az is real. Every eigenvalue of a Hermitian matrix is real. This is a fact. And as a proof, suppose Az equal to lambda Z, okay? Multiply both sides by Z Hermitian to get Z Hermitian Az equal to lambda Z Hermitian times Z. Now, the left-hand side is real, and the right-hand side, Z Hermitian times Z, is also real. So lambda must be real. Take an example for a Hermitian matrix A. The determinant of A minus lambda I equals 0. So we calculate the lambdas. We get characteristic determinant is lambda squared minus 7 lambda minus 8 equals 0, which factors into lambda plus 1 times lambda minus 8 equal to 0. So lambda 1 is minus 1 and lambda 2 equals 8. The eigenvectors of a Hermitian matrix are also orthogonal provided they correspond to distinct eigenvalues. For example, if Z is an eigenvalue of A and Y is another, Z is an eigenvector of A with eigenvalue lambda, and Y is another eigenvector corresponding to another eigenvalue beta. So Az is lambda Z and Ay is beta Y. Then Y Hermitian Z equals 0. To prove it, multiply Az equal to lambda Z on the left by Y Hermitian. Okay, so Y Hermitian times Az is lambda times Y Hermitian times Z. Now for the second one, if we take Ay Hermitian, it becomes Y Hermitian A Hermitian equal to beta times Y Hermitian. Okay, from this one. Now multiply it on the right by Z, becomes Y Hermitian A Hermitian Z equal to beta Y Hermitian Z. But since A Hermitian is equal to A, then the left-hand sides, both equations are the same. So we have lambda Y Hermitian Z equal to beta Y Hermitian Z. And since lambda is not equal to beta, then Y Hermitian Z must be 0. So they are orthogonal. That proves that the eigenvectors of a Hermitian matrix are orthogonal if they correspond to distinct eigenvalues. For the matrix in example 3 above, the eigenvectors are solutions of A minus lambda I times the vector Y, for example, or Z equal to 0. And if we solve for the in case lambda equals -1, we get the first eigenvector y as 1 minus I minus 1. And for the second eigenvalue 8, so it is a minus 8I times z equals to 0, and it gives z equal to 1 plus I. So if you calculate y Hermitian times z, it is 0. So the eigenvectors are orthogonal. These eigenvectors are not orthonormal. They can be made orthonormal by dividing by the norm of y, which is √3, and the norm of z, which is √3. So S, the eigenvector matrix, goes to Q, but Q here is complex. Now, we look at unitary matrices. A unitary matrix is a complex square matrix with orthonormal columns. It is denoted by U, so it is the complex equivalent of Q for real matrices. So for the last example, U is 1 over √3 times y and z, and it is a unitary matrix. This U is also Hermitian by accident. You know that any eigenvector can be multiplied by any number and it is still an eigenvector. Magnitude changes but direction not. Here, if we multiply by 1 or -1 or by I, the matrix is still unitary, okay? But it is not Hermitian, okay? If we multiply by I or by -1, the matrix is unitary because it satisfies U Hermitian U equals I. This is the matrix test for real orthonormal columns. In the case of real matrices, okay, it was Q transpose Q equals I. Now for the complex case, it is U Hermitian times U equals I. And you can check it for this matrix. This is U Hermitian times U, and we get I. So now another fact is that if U is unitary, then UZ, the norm of U times Z, is equal to Z, the norm of Z. Okay, so UZ equals lambda Z if Z is an eigenvector. So the eigenvalue lambda must be of magnitude 1. A proof, if you take UZ squared, the length squared of UZ, it is Z Hermitian times U Hermitian times U times Z, but U Hermitian U is I, so it becomes norm of Z squared. So if Z is an eigenvector of U, this means that lambda, the eigenvalue, has a magnitude equal to 1. So the eigenvalues of unitary matrices have absolute value of lambda equal to 1. That concludes the course.